Consensus building in online citizen science. Citizen science and crowdsourcing projects use paid or unpaid volunteers for classification tasks as the internet provides the opportunity to collect or annotate data on a large scale. Typically, multiple annotations are requested and a minimum level of consensus is expected. Annotations are either independent or through a collaborative interface, and platforms provide users a means to share knowledge, either on the task or through forums. However, there is limited understanding on how collaborative design affects users' behavior and whether these techniques can be used to improve data quality, engagement, and learning around the task. We study the design of interfaces that allow volunteers to collaborate on classification tasks. For the task, we used a citizen science project which helps users to submit and identify bumblebee images using an identification key. The species can be differentiated based on color band patterns, presence of pollen baskets, and face size. All the images had 10 independent IDs, and we only selected images where there was a lack of consensus. Additionally, we identified three situations where crowdsourcing did not provide a consensus. Firstly, if there was an existing majority towards the correct ID, that is 5 out of 10 users identified the image as a single species and that species was the correct answer, we labeled these as consensus correct. If there was an existing majority towards an incorrect ID, we label these as consensus not correct. If there was no majority, we labeled these images as no consensus images. Interfaces for collaboration. The level of agreement on a task is often utilized in online communities for problem solving and decision making. To determine whether information on the existing distribution would influence participants, possibly towards the majority opinion, distribution was used as one of the techniques in the form of a pie chart. This interface did not include specific guidance from others to reduce the number of options, but largely reinforced existing knowledge. Ratings of user expertise are also widely utilized in online communities, and this second interface was developed to assess the effect of expertise of other participants. In this interface, 10 anonymized species IDs were shown as a list with ratings. Participant-owned ratings were not displayed in order to prevent comparison of their own expertise with others. Blue bars represented experience, golden stars represented skill level. Sharing of resources through communication is important for building communities, and projects use this method to capture expertise and to provide opportunities for experienced individuals to guide others. We designed a third interface whereby members of the group could effectively communicate their knowledge using anonymous, goal-directed comments. The user firstly highlights the user's identification and the alternative identification provided by others. The user were then encouraged to leave anonymous comments, specifically focusing on the features that may help others. It was also highlighted that they could read existing comments. The interface fosters a dialogue between participants by using specific features that they consider significant for identification. Lastly, we utilize the natural language generation system to study the role of AI for supporting online collaboration. The system provides machine-generated texts highlighting any differences in visual features between the different species. The interface first highlighted the features of a user's existing identification. Next, the text reported differences between user's ID and each of the conflicting identifications. Procedure: participants with previous identifications for the selected photographs were emailed to review their identifications. The users were shown a list of images to review, and clicking on one of them would lead to a collaborative interface associated with that image. The user could review the information and click review or not review. If they clicked review, they were then shown the collaboration interface and the identification interface to review their ID. Reasoning behind the reviewing or not reviewing was also collected for qualitative analysis. Results: the majority of images for which participants clicked review were initially incorrectly identified, and majority of images not reviewed were initially correctly identified. Thus, incorrect identifications were more likely to be reviewed during collaboration. User ratings was the most persuasive, followed by social and NLG. Distribution interface resulted in lowest percentage of identifications reviewed and changed. This figure shows how the level of consensus changed from before to after collaboration across all interface types, and there was an increase from 58.2% to 67.6%. The third figure shows the mean percent changes in accuracy across interface type and consensus type in the first three columns and overall change in the last column. User ratings were most sensitive to consensus type, improving accuracy for only consensus correct images. Overall, the social type achieved greatest accuracy, followed by NLG and user ratings, with low level effect of the distribution interface. Qualitative results. Distribution interface was least effective in making participants review identifications. While this interface gives information about the existing disagreement, if it offers limited opportunities to engage in a dialogue. The interface relies on participants' self-motivation to review, as seen from the comments. User ratings were persuasive and made participants review their IDs. The participants were not aware of their own ratings. It emphasizes how the perception of expertise can be used to improve engagement. Using the social interface, participants could could provide reasoning behind their identification as well as learn from others, including if they had overlooked certain features. The comments left suggested higher engagement with the overall process of identification. Participants provided information that is difficult to capture using other interfaces. The interface promotes dialogue, and the information provided enable, enabled convergence of thinking. The NLG interface was designed to provide a comparison of identification features. It simulates a dialogue, and comments often focused on features that were clearly visible in the image and may have directed attention of users towards those features. We we investigated how participants involved in a citizen science project responded to different forms of feedback. To address this, we designed four interfaces implementing feedback mechanisms in the form of majority vote, user expertise, communication and sharing of resources, and NLG texts representing expert knowledge. We found that interfaces which support and logical reasoning for problem solving, such as social and NLG, are more effective than the ones which only display consensus and user expertise. User expertise influences participants to carefully reconsider their choices. However, they should be approached with caution. The social interface was most effective in improving performance and engagement. The effect of AI in mediating collaboration tasks using the energy revealed that it was on average as effective as the user ratings, and the effect was consistent across all consensus types.